with the topic signals and systems. In signals and systems, we'll be covering various types of signals, classification of signals, the various elementary signals which are there, which we'll be considering in our course, the basic operations which are dealt with different signals. Then we'll start with the other topic systems and types of systems. In system, we'll be mainly considering LTI system, linear time invariant system, and their properties. Now, starting with signal. Now, if you take a signal, now basic definition of a signal is any information or any quantity or any magnitude which gives you some information is a signal. So, and it is dependent on one or more independent variables. So, now if you take an example of a current, like in terms of in electronics, usually with current, voltages, so they are dependent on, like if you take a equation of voltage, V is equal to IR, which is the basic Ohm law. So what is Ohm law? Now over here we assume that temperature remaining constant. Now if you assume R is constant, so my voltage, the signal which I am getting through my multimeter, is dependent on current. So current is my independent variable, and this current, if it is a AC signal, is dependent on time. So your basic independent variable is time, whereas in general, like if you consider only in terms of voltage, the independent variable is current. Now various classifications of signals which will be dealing, like the most common one is the digital or analog. Now if I take any signal, now whatever signals which are there in nature or whatever we see, they are all analog signals, like continuous signals. So like if you take an example of a sine wave, it's an analog signal. Why? Because it's we measure it with an analog device, it's continuous. Digital signals are signals which are there, usually what we see in our computers or logic circuits, which are having some weightages. Like if you see binary. Now the same signal can be expressed in terms of binary. If I say yes, the first I need to discretize it, so I get the signal. Now I can weight them. Like I can say this first is 0, 1. Second is 1, 0. The maximum amplitude is 1, 1. So I can give them digital values. Then the second classification, which is another common, is continuous and discrete. Now, continuous signal, as we saw, like an example of a sine wave, it's a continuous signal. Or you can take any arbitrary waveform which is there, it is continuous. Why? Because I can find out the value, or you can say amplitude or the intensity at each point. If this is a time scale, so I can find out it if this is 1, 2, 3, so I can find it 0.1, 0.01, whatever values. That is continuous. Whereas if this same signal, now the problem with continuous signal is when you want to store the signals, it's difficult. We require lots of space. Now, if you know in computers what data, CD-ROM or hard disk, we sample this signal. Now, if I take the same waveform over here, I sample my original signal based on some sampling frequency. Now, if I take this is my interval of sampling, so I get one output over here, another signal over here, third here, fourth here, and accordingly. Now if I take these are my discretized signals. Why? Because I have divided my continuous domain into some discrete points. I can find, if I say this is 0, this is 1, 2, 3, but I cannot find a value at 0.1 because I have discretized it just for storing, because continuous signals are difficult to store. So discrete helps me, like we know there are structures and arrays in C language. So this data can be stored in such arrays, which will be easier to interpret. And also it requires less space compared to storing a continuous signal. For discretizing, we use some sampling frequency. So usually based on IISc criteria, the sampling frequency is twice sampling frequency, it should be at least greater than twice of your signal frequency. So if your signal frequency of a sine wave is suppose 50 Hz, so your sampling frequency should be double. Okay. So if it is not there, then it will have some errors in sampling. The signals won't be proper. You cannot, because this sampling frequency is important, because like if suppose I'm transmitting some signal to some distance. Now the person over, now there is a receiver over there, super heterodyne receiver, some receiver which is there. It is receiving my signal. Now it is taking the discrete signal. Now with the discrete signal, the first frequency value or first discrete value is usually the frequency. Okay, what frequency the signal was sampled. So based on that, my receiver will reform the whole signal again for display again when you want to see at the output. So if my sampling frequency is not greater than equal to, or if it is less than the signal frequency, there will be aliasing effect. Then the third classification is causal, non-causal, and anti-causal. Now any causal signal is a signal which is depend on present and past inputs. Like it requires present and past. If I take an example, if there is a signal yt, it's dependent on it's a cos 2 pi t. So if I'm at an instant of time 1, so if time is 1, so here also I'm depending on my present input. Now suppose there was instead of cos t, okay, there was another term cos 2 pi t minus 1, and I am taking the signal at an instant t equal to 3. So it becomes y3, which is equal to cos 2 pi cos 6 pi plus cos 2 pi. So, or if you take in terms of its cos 2 pi at time 3 plus cos of 2 pi time 2, 3 minus 1. So it's dependent on my either past or present. That is the causal signal. Now the second one, which is non-causal. Non-causal, it's like an extension of causal. It will have all the properties of causal, like all the input. Like it will have present and past plus future input. Now you might think how you can get a future input. When you are like, if you take an example, when you are doing a digital signal processing, now the system, now it goes to a particular position. So take an example of an array. Now array has, this is the 0th position, this is the first position, second position, third position. Now if I am at instant at array 1, like if I take, and this is my array A, I am going to the position 1, this is like the second position if you come in 0, because it starts with 0. So I am over here, somewhere over here. Now I can go back and I can go front. So from, if I assume this is my present, going ahead is going to my future inputs, going back is going to my past input. So over there, when you are modeling a system based on that, there you take into consideration your future inputs. And also many filters, which are digital filters, one of the common example is adaptive filters. Adaptive filters take into consideration the future input. Like, well, it's modeling, there is a feedback path. So it's like there is an when you design it theoretically, you consider, okay, there will be error, there will be some error in a range of plus minus so much %. So you by default give it an input, which is like you can consider that as a future input. Then the third one is anti-causal. Anti-causal is, as its name signifies, it is opposite of causal. So causal contains present and past. Present, past. Non-causal, present plus past plus future. Anti-causal is only future, no present, no past. So if you want to write in terms of an equation, I can write non-causal signal is a combination of causal plus anti-causal signal. So moving towards the fourth classification, which is periodic and non-periodic. As the word periodic signifies, periodic signals are signals which will repeat after some interval. So if I take an example of a sine wave, like sine wave has some frequency, and after, like, based on that it will repeat. So if I take this interval as 5 seconds, so after every 5 seconds the same signal should repeat. That is, if this 5 seconds, this value 5 is my period of this particular sine wave. And non-periodic is the signals which will not repeat. Like, if you take any noise signal, noise is like, it's some arbitrary signal. You cannot say when it will repeat, what will happen. So it's like it's an aperiodic signal or non-periodic signal. Now, if you consider equation like yt is equal to some amplitude a cos omega t. This is a cosine wave with an amplitude a. Now I want to find like a period for this. Like, how do I find out what is my period? So you take this omega. So you know omega is 2 pi f. So whatever value is there, you divide, like in the coefficient of t, you divide by 2 pi, and that is your that is your period. That is your sampling frequency. From that you get your period. So that basically you can say that is a frequency. When you are in continuous, it's a frequency. When you are in discrete, it's a sampling frequency. Now moving towards, now if you take an example in discrete, same thing, yn. Now in discrete we'll write a cos some value. If I take 2 pi f n, and let's put some phase. Okay, so this is my frequency. There is some phase. Now I want to find out what is the period for this equation. So for, as we define, periodic, like it will repeat after a particular interval, and then, like you say, the basic period, or you can say the natural period, will be like the smallest value. Like, because if you take an example of the sine wave again, it will continuously repeat. I can say this, instead of this 5 seconds, now this 5 seconds is the basic period. Again I can say 10 seconds, after every 10 seconds also this wave is repeating. After every 15 seconds also it's repeating. But the basic is 5. I cannot say 2, after 2.5 the wave is repeating. After 5 seconds, so this is my basic, or basic period. Similarly, over here, I want to find out what is my period in discrete. So what I'll do, I'll take some value n. So like n plus some capital N. I'm assuming this is my period. Now, further simplifying, I get 2 pi fn plus 2 pi f capital N plus theta. Now, what I want, this signal, which is like n plus capital N, this y n plus capital N. Now, this signal y n plus capital N should be equal to my original signal, because it is periodic. So after this, it should repeat. So for this condition to be satisfied, this factor, like if you know, like cos of 2 pi plus theta is cos theta, or any like cos of, in general, if you write in terms generally, it's 2 pi k plus theta, where k is any integer. K is an integer. K can take values from 0 to n. So over here, now this is again cos. So this will be, now this 2 pi fn has to be an integral multiple of 2 pi k, where k is an integer. Now cancelling out 2 and pi, so my frequency is equal to k by n. So if I take any discrete signal, and if I find some its frequency, which can be written in terms of ratio of two integers, because as we saw over here, k is an integer, it will take values from 0 to 0, 1, 2, 3 to n. And again, n should be an integer, because we need to get a finite period. We are in discrete, we cannot say it's 2.1. So we want this ratio in terms of discrete, in terms of integer. Now taking an example, Now if I take a cos wave in discrete, cos of 2 pi n, 2 pi n. Now I'm comparing it with our original. So I'll say this is my omega. So 2 pi is equal to 2 pi k, 2 pi f. So f is 1. So it is basically like I can write 1 as 1 by 1. So there are two. So it's a ratio of two integers. This one is an integer, another. Basically ratio of two rational numbers. Now taking another example, cos 0.01 n. 0.01 n. Now again comparing 0.01 with 2 pi k, 2 pi f. Sorry. So f is 0.01 upon 2 pi. Now we know pi is like it goes from 3.14. Usually we use 3.142, but actually it goes to some, like many people for different application it goes, you take different decimal values. So this is not a ratio of two irrational numbers. So this is aperiodic. This will never this wave will never repeat. Now the same signal, I'll take 0.01 pi n. Now 0.01 pi is equal to 2 pi k. So again pi cancel, k is equal to 0.01 by k. Now you might think, okay, there's a decimal point over here, it cannot be a ratio of 2. But I can write this 0.01 upon 2s, 1 upon 200. So it's a ratio of two numbers like 1 and 200. So it's periodic. Now moving ahead to the energy and power signal. Now usually we write, and when we take alternating current in AC, we take instantaneous power and average power. Now if I take the same basic example what we like, there is a resistor. Suppose there is a resistor. Suppose there is some resistor. I'm passing in current IT, instantaneous current IT. Now if I want to find the power or over at this point, instantaneous power. So what will be the equation? I square T R. This is resistance R. Okay. I square T into R. Now this is my instantaneous power. I square T into R. Now when you compare relation of energy and power, so what is power is energy. Power is energy by time, or energy is power time, power into time, whatever you represent it. Now the application, like why do I need to divide my signal into energy and power? Now if you take an example of transmission, like if I want to transmit my signal to far different, like if you take an example of your networks or the satellite. Now there's a main satellite which is rotating around the earth, it is revolving around the earth. Now from there the signals are being transmitted to us. Now there are something called adapters. Now suppose I want to transmit from my home some signal toward a far distance place. Now after some time, because of walls and trees and mountains, whatever obstacles which are there in between, the frequency, the amplitude or intensity will go on decreasing. Like many times you experience, like in an area, like especially in basements of a building, you don't get network because there is so much, the thickness of the wall is thick enough to cancel the signal, or the intensity of the signal becomes so low that your cell phones cannot detect. Similarly, like we need to know, okay, what is the energy and power? So at how far should I have my adapter? Adapters are, you can say, they take the signal. Like if I'm transmitting some signal, there is an adapter after a distance of 5 km. It will receive the signal. It will again amplify it to the value based on where there is the next adapter or where is the receiving station, and send it further. So this energy and power signals, like we need to find out, okay, what is the energy and power for such application. Now, if you take some equation, like take our normal xt is cos omega naught t. Okay. Now I want to this xt is cos omega naught t. Now if I draw the signal, so my cosine signal will start from some amplitude, it continuously repeat. And like we are assuming that we are at 0 position signal starting. But if you take a continuous, it goes, if you take a general cos signal, it will go in the negative axis also. Like the previous, this is like the future, this which is gone. Okay. So this is my cos signal. Now it will extend, like if I don't put some domain, if I don't limit it to some domain, it should extend to infinity. Now when I want to find out, you can say energy. Now what I'll do, I'll sum it over, like if it is discrete, I'll sum it over. If it is continuous, I'll take an integration. So like it becomes energy is integrating from some interval. I can say minus t by 2 to t by 2, and whatever is the signal xt, square of it dt. Because it's an integration with respect to time, and where limit t tends to infinity. Because we are considering from throughout the range, so it will go from minus infinity to infinity, square of the signal, and integrating it, so it will get the energy of the signal. Now similarly for discrete, in discrete I think it will change this only this integration sign will be replaced by summation, because it's not continuous and integration is defined for a continuous. So your signal value will vary from minus t by 2 to t by 2. Your limit t tends to infinity, square of the signal. Now while consider in case of a complex signal, that's why we usually consider the mod of the signal. So in general, if I want to write the equation of an energy, so I write mod xt square dt. So even if I am some complex, so I convert it into convert it into rectangular by using the formula for mod. In case if you don't know, if you take a complex signal A plus IV, the mod will be root of real square plus imaginary square. So we are trying to remove that imaginary part from here.